In the study of statistics, it is important to be able to differentiate between a population and a sample. A population would be all of the objects of a given characteristic. For example, all of the U.S. senators. We could study maybe the age of all of the U.S. senators, and this would be data that would not be difficult to get. I'm sure that if we did a Google search, we could come up with several web pages very quickly that would give us the age of all of the U.S. senators. It's a relatively small group and well documented. However, if we wanted to come up with the age of all of the U.S. citizens, well, that would be much more difficult to come up with and would in fact be impossible to come up with, as that is a constantly changing data set, and there would be no way that anyone could collect data quickly enough to get a snapshot at one moment of the ages of all of the U.S. citizens. So in a case like this, a sampling would need to occur, where a sample is a subset of a population. So in order to come up with an estimate then of the U.S. citizens, we would have to sample, but we would have to sample in such a way that each element of the population would have an equal probability of being included in the sample. There are techniques that allow for this kind of condition, and when this condition is met for a sample, it is considered a simple random sample. It is important that samples are random in order to avoid different kinds of bias in a set of data. For instance, we wouldn't go to an elementary school to find the average age of U.S. citizens. Obviously, our data set would be very small compared to what would be a better representation of the ages of the U.S. citizens. Likewise, we wouldn't go to a long-term care facility that catered to the elderly in order to get a data set that represented well the ages of the U.S. citizens, as that data set would contain data values that are much larger on the whole than the actual population itself.